Hi, we're SternCorp, and we've developed what we believe is a game-changing sternum prosthetic for North American patients who undergo a sternectomy procedure.
You may be wondering, what is a sternectomy? Sternectomy is the removal of the sternum bone. It is usually done to access the organs underneath. Thus, it is essential to some surgical procedures, especially open heart surgery. It is typically a relatively long and complex procedure. Most of today's methods for sternectomy require hours of intensive surgery. Here are some statistics related to sternectomy. 2.5% of all bone cancer cases are sternal cancers related to sternal chondrosoma, which requires full sternectomy. This percentage is confirmed with a study of 309 patients with breast cancer showing 5.2% incidence of sternal affection. The biggest incidence of full sternectomy actually comes from victims of car accidents, where 9% require the procedure for chest wall reconstruction. Some risk factors associated with complications of the sternum post-surgery are obesity/high body mass index, diabetes mellitus, prolonged cardiopulmonary bypass surgical time, osteoporosis, in this case causing decreased sternum thickness, cardiac reinfarction, and emergency surgery. The scope and objective for the project is to meet the necessary constraints and criteria, to evaluate and compare our design to alternative designs, to calculate the physical properties of our proposed device, and to determine the overall cost for the device.
Approach for the design process required preliminary extensive research and creative brainstorming, as well as tools like SolidWorks and Excel to make possible the creation of a definitive prosthetic model in 3D with defined mechanical properties. Their preliminary research was consisted of current alternative methods used for full sternoctomy, legal and manufacturing requirements, different biomaterial possibilities for the device, and a professional transcript from a thoracic surgeon. All these researches boiled down into the creation of the design constraints and criteria for the device. The professional transcript from Dr. Javier Triana, a thoracic surgeon from Colombia, determined that biocompatibility, biomimetic function, modularity for surgical complications, aesthetic looks, and user-friendly to the surgeon and patient involved are the key points to follow to create this medical device. With this in mind, a design matrix was created and used to evaluate 3 different preliminary designs, which ended up into a final design proposal. All previous research considered, it was determined that all current methods regarding this issue are limited due to high cost and causing multiple affections after surgery. Some key examples were brittle bioceramic plate-based methods with low flexibility, or wire-based methods cutting through the sternum and only achieving sternal unity of 24 to 70%. Using ISO standards and the previous research, the key characteristics for the materials will be biocompatibility, high flexural strength for rib cage movement, and enough impact strength to protect internal organs. This is how the ribs become of high compressed plastic and the body of alumina. With that being said, the key issues regarding this model were avoiding multiple surgeries, the structural integrity of the device at real-life case scenarios, materials with specific mechanical and biomimetic properties, high surgery costs, and different sized patient sternums. Having this in mind, the problem statement was the following: to design a prosthetic to be used by surgeons to replace the sternum of sternoctomy patients, which provide protection to the chest region, help retain the quality of life, and enhances the well-being of patients over a long term. The first proposed design has a mechanism which uses a slide principle for ribcage expansion, allowing motion of the ribcage with ease. Device implementation will be bolts against the rib, but the issue with this could be continuous buildup of friction of the mechanism, so long-term usage can cause structural failures which can endanger the patient's well-being. This design advantage are high lifespan and safe weight. However, though any impact can cause a mechanism failure which can be catastrophic to the patient. The second design consists of a hollow body with the top part of the manubrium and the ribs. The connections between top and body are by ball and socket, and the ribs connect with the trigger mechanism, which acts as a hand clamp, attaching the ribs with the body. The principle from this proposal is the insertion of bone fragments from the sternum into the chamber part of the body, and making possible for bone to grow with the device. However, this design has the least amount of flexibility. Also, the sternum grows in an unpredictable way, and it can put stress on the titanium cover. Design 3 is based on personalized prosthetic parts connected through a series of caps to create a device with the patient's measurements on the spot. Top and bottom were designed to conform all different size users, making it versatile to use in any situation. The insertion against the ribs will be through bolts. The body is made of a strong bioceramic to imitate the function of protection of the sternum with the internal organs. The advantages are best flexural modulus, good lifespan, appropriate weight, and economic cost. And even though its insertion involves bolting with a log grafting bone, which is a complex procedure, its degree of complexity was smaller than the other designs.
The next step then is to take those preliminary designs and evaluate them based on the design constraints and criteria. Looking at the constraints, they're focused around making sure the device does not harm but aids the patient, noting key constraints like making sure the device is bioinert and that does not hinder the motion of the patient and can withstand the same impact force as a natural sternum. And then switching gears and looking at the criteria, they're more focused around optimizing the device as much as possible. Where again, key criteria are focused on matching the physical attributes of a natural sternum, seen in the maximization of the flexural modulus of the device and minimizing the weight difference between the device and a natural sternum. These criteria were then used to make a decision matrix, with criteria relating to the physical attributes of the device weighted highest. In this matrix, we could then see that design 3, the device using a system of caps, was the ideal choice to move forward with. The next step was material selection, for which we chose a ceramic for the body and caps, which was alumina, and we chose the plastic compressed polyethylene to serve for the arms. We chose these materials as they were all bioinert and gave us the physical properties we wanted for a device to replace the sternum. With all this said and done, the final device chosen was a mix of a ceramic base with plastic arms. The key to the design is interchangeable ceramic caps to act as extensions to the base of the sternum, as well as a variety of plastic arm sizes that allow the device to fit both wide and narrow chests. The goal is that the device will be sold as a prepared kit, including a variety of caps and arms. Thus, the surgery team can assemble an appropriately sized sternum based on measurements they've made in the surgery theater. Once assembled, the team can then bolt the arms of the device onto the ribs of the patient, creating a strong prosthetic with a wide range of compatibility. We then performed a mathematical analysis to make sure the device had the physical attributes to properly replace a human sternum. The analysis proved it would be an ideal solution. The specific focus on the high impact strength of the center plate, the minimal increase of mass of the device compared to a natural sternum, and a fatigue resistance of 13 megapascals, meaning any repeated loading under 13 megapascals will not cause the device to fail.
The sternum prosthetic allows the user to live a healthy lifestyle and have no hesitation when it comes to playing sports and being active. The prosthetic provides an increased protection of the chest area while allowing a full range of upper body motion. The sternum prosthetic gives users an increased protection, all while keeping the flexibility in their chest area. The prosthetic is designed for long-term use and will not be in need of replacement due to gradual wear. Doctors will be given a sense of relief as they know the patients who receive the sternum prosthetic surgery will not have their organs left in a defenseless position. Society as a whole will feel better off knowing that if they are in a serious car accident or require a sternectomy surgery, they will not have to radically change their physical regimen. The cost of the materials and manufacturing per prosthetic is estimated to be $9,500. This is impacted by the precision required when manufacturing. For perspective on price, the materials and manufacturing cost per hip replacement is estimated to be $12,063. SternCorp's engineering team's work is $154,206. The price per prosthetic will be $11,875, which has a gross profit margin of 20%. Since the prosthetic is designed for long-term use, there will be insurance available if the prosthetic is broken due to gradual wear. The sternum prosthetic is not designed to experience forces over 4,000 newtons, as the factor of safety is only 1.0226 at that point. Larger impact forces will cause a great bending stress on the prosthetic arms, and if they fracture, the user will need surgery to fix them. The system boundary shows a straightforward process from extracting the materials to the prosthetic being recycled after many years of use. The life cycle inventory has a very simple input and output system for this specific project. It is important to note that this product has very minimal environmental impact, and all of the materials can be recycled and reused in the future.
Quality control management system is mandatory. It's going to abide with ISO and Canadian government regulatory requirements. As shown in the quality matrix, quality planning has the objective to define customer and product design requirements, such as inconsistencies that can affect the patient's well-being or high manufactured parts will ensure less complexity for the surgeon to implement on the device. Quality control uses automation to avoid any dislocations in the materials involved, ensuring structural integrity. Quality assurance consists of quality control managers, engineers, and technicians for the machines involved, which will increase the rate of noticing small faults in the device. And lastly, quality improvement is ensured through routine checkpoints of the machine to ensure no existence of non-conformances.
As we go forward, there are risks and uncertainties that present issues. To start, any unanticipated stress concentrations may cause the device to fail, and as such we will need to have a thorough round of laboratory testing before the device is made available to the public. As well, any abnormalities in the chest could render the device useless. If the patient's chest grows, this also presents an issue, and currently we only have hypothetical solutions to modify our device. And lastly, we have to develop a way to educate surgeons before the operation, whether that's an instruction manual or a course, so that way they are aware of how to use our product. As SternCorp looks to the future, the first step will be the production of a prototype, so that way rigorous laboratory testing can start. Once this is completed, SternCorp will then need to begin the process of acquiring a medical device license. The device is considered a Class 4 medical device, and therefore SternCorp is going to need to acquire a medical device license so that the device can be legally manufactured in Canada, as well as a medical device establishment license in order for the device to be legally sold inside Canada. Once SternCorp has acquired these licenses, we can then begin human testing and then production of the device. Once the device is in production, we can then start to explore different avenues to expand the range of the device, such as using a segment of the memory metal nitinol, which would allow the device to grow with the growth of the human chest using the body heat of the patient. To summarize, there is a notable population of patients who risk having their internal organs unprotected due to sternectomy procedures. Thanks to the unique system of cap extensions, SternCorp has developed a device that not only reduces the price, it provides the same protection as a natural sternum and lets patients return to an active lifestyle, improving the overall quality of life. As such, we recommend that after proper testing takes place, this device is introduced to the Canadian market and potentially all of North America down the road, so it can begin changing lives. Thank you very much.